Okay, thank you very much for giving me the opportunity to talk about this space-based laser frequency comb. It's a completely different topic what I used to do, so I'm not sure I'm really competent, but it's a crazy idea. I thought it would be really the right place to present here. Okay, so you know all this, and I take the opportunity to show this nice movie by Sam Halverson. He showed that EPR4. Okay, the technique of radio velocity is to find Earth, or let's say extrasolar planets, where you project the spectrum of a star somehow from the frequency space into the wavelength space, as explained by Suvarat. So we have to convert it because we do not have enough photons to do heterodyne detections on star. So we have to convert into the wavelength space, and that's what you see here. And every conversion into the wavelength space, you have then to recover the wavelengths, and this means that you need a calibration to do that. So the wavelength calibration is really one of the major steps to go here. And what you see on the top of the star spectrum is a ruler, is a laser frequency comb spectrum. Here it's on fiber B, which is on a second fiber, which is used to monitor the drifts of the spectrograph. But what we are interested in is to use it on fiber A, so on the measurement fiber, to calibrate the observable, so the measurement, the astrophysical measurement. And as mentioned already several times, we normally do not care too much about accuracy. I mean, the absolute wavelengths you get from that, because normally you focus on a time sequence, which is, and you want to see relative radial velocity changes. You are not really interested in absolute changes. So there are many reasons why you could be interested in accuracy as well. We were talking about the gravitational redshift. There are other science cases like Sandwich test, but even for planets, we may be interested in accuracy. And the reason is for this is here. So you see on the plot top right, a shocking experience I made with the HARP spectrograph. When we changed the fibers, we had efficiency, not issues, but they were not super efficient. We had scrambling efficiency with the old fibers, the circular fibers. So we changed the fibers in 2015. And after changing the fibers, we discovered, I was convinced that there would be no impact, but eventually we saw that there was an impact on the radial velocity we were measuring from stars. So there was an offset in radial velocity. And what you see here on this plot is the offset measured as a function of basically V sinus I, or the full Wisdorf maximum of the cross-correlation function. And the wider the cross-correlation function, the more important the offset. And we are talking here about 15 meters per second, which is really well beyond what we want to reach with a spectrograph like a HARPS, where we aim at the 1 meter per second. So after a little bit of thinking, we came to the conclusion that this was due to the fact that the IP is not, I mean, has its own life, the instrumental profile, so it's asymmetric, it has a certain width, and that's the whole process of measuring spectra is a convolution at the end between the stellar spectrum and the instrumental profile. So we had just to cope with that. That's it, that's what you can get. But the question is, what happens if you have a problem with the instrument, if you want to ensure, let's say, repeatability over many years, and you cannot guarantee that there is no change in the instrument or any other drift in the instrumental profile. So here, two aspects came in. The one that we have a laser frequency comb, or we will have laser frequency comb, which provide known spectral lines of not infinite, but very, very narrow width, which basically perfectly resolve the spectrograph instrumental profile. The other idea is that in order to ensure repeatability independent of the instrument, you need actually a method to be accurate. You have to be able to refer always to the same standard. So the accuracy is actually, in my opinion, the best way of ensuring long-term repeatability, independent of the accuracy itself. So there came two others idea, and is the fact that our calibrators often do not actually measure the whole system. So for example, for espresso, we inject the calibration source very late in the system, in the coup de passe, and so you don't have the whole coup de passe, the telescope, which is calibrated. So here we would like to propose an artificial star where you feed with the calibration source directly the whole system. And the other aspect is that we have no guarantee or no mean that we can link together different measurements from different instruments over a long time span. So here again, if we had an external calibration source which would be accessible to all instruments, all observatories, for example, from space, they do solve the questions of longitudinal coverage, sampling, and time span. So that's the idea, having a satellite on a near equatorial orbit, which would move in a way that it would be accessible at least once per night by any observatory in the world, or any major observatory in the world, so within plus minus 45 latitude. So the stationary visit time should be about 12 hours, and we should avoid too low air mass, or too high air mass, sorry. So that's really the key point. A satellite which would be some kind of global wavelengths calibration service to any observatory. That's the system we imagined, a laser frequency comm module on a satellite to as light as possible, power consumption that would be affordable for this kind of satellite, maybe having, okay, it should have maybe the correction for, so knowing its velocity such that it could correct on the laser frequency comm lines the velocity, such to provide already constant reference. But okay, this can be also corrected also a posteriori if you know the speed and the position of the satellite. And of course, data transfer and so on. The laser frequency concept is the one that we all use. So we want to have accuracy. We want to have, through accuracy, stability, narrow line widths, dynamical range, which is affordable and, I mean, not too high, and of course, covering the wavelengths range we need for the spectrograph. And these are, let's say, standard specs. How we want to achieve them is that we want to use actually an electro-optic modulation for producing the comm lines, such that we do not rely on, for example, cavities that must be stabilized in the satellites, vibrations, things like that. So this would be fully integrated electro-optic system on all by fiber or integrated optics. So very robust, very reliable. We would probably aim at a medium Earth orbit, so at between 10,000 and 20,000 kilometers, in order to get this 12 hours desynchronization and rotating in the same direction of the Earth, such also to avoid too high speeds for the telescopes to slew and track with. I don't go too much here into the mission concept. We are just starting thinking about that. It's the difficulty will be to place these in MEO, so in a medium altitude orbit, because there you have radiation problems. and it's the price of this rockets or to bring the satellites there will be quite high. So we have to think about whether we could have in a piggyback with other missions, maybe on the orbit of the Galileo GPS system, something like that. So we are really thinking how to optimize the difficulties and the costs of this mission, which is not a minor problem. So I will stop with this slide here, which is basically the challenges we will have to face for this idea. And as I said, we just submitted to Prodex a proposal. We're still waiting for the response. Hopefully this will be positive. And during this study, this pre-study, we will have to choose the right orbit, which will imply discussions about shielding, weight, mission costs, and so on. The reliability of the LFC will be a major issue. Power consumption, of course, of the satellite. The tracking, slewing capabilities of the telescope. We have to be able to follow this satellite. And there is a trade-off between power and so footprint on Earth and the ability of the satellite to point the observatory in order to get the light into the telescope. This is a major question. And of course, we have to understand how we can correct, or we can know exactly the precision, the speed and the position of the satellite at 1 centimeters per second and 0.1 arc second, such that we can know its relative velocity with respect to us. And that's it. So it's a lot of challenges, and then I take questions if there are any. Thank you for your.
Thank you. All right, questions. There must be a ton. Okay, in the back.
Hi. Yeah, very ambitious and nice project. I would love to have that. I wonder though, if there were fully integrated LFCs with those features you would like to put on the satellite, wouldn't they be so cheap then that you could actually just distribute them directly to the telescopes because they are so readily available?
So basically having an LFC at every observatory.
Yes.
Yeah, I think that, I mean, that's the alternative, of course. Again, I think that the idea here is to have the same calibration source for all the observatories. So I think it's not exclusive. I mean, the two things are not exclusive. And anyway, the satellite will not be available all the time. So this would be, for example, a possibility to lock or to reference any calibration source locally to a global standard that would allow also to link together all the spectrograph. I'm not sure we are yet in situation to be able to really retrieve, I mean, to be sure that we get all the instruments calibrated. There will be another presentation bit after that by Tobias Schmid, will present the question of absolute calibration accuracy. So there are many, many questions. I think having the same source for all the instruments is one of the solution. It's not the only solution, but it's certainly one of them.
Okay, just a quick check to see if we have any questions online. Okay, hang on a second. Okay, no question on. Okay, one quick question from Chaz.
Doesn't the fact that all the laser frequency combs reference back?
It's on. It's on. It's just hard to hear.
Oh.
Hold on.
Doesn't the fact that the laser frequency combs all tie back to GPS and basically then back to an SI second give you that absolute temporal calibration that we want? I mean, that links all the observatories' absolute calibration together through the GPS system.
Yeah, I mean, I think this is part of the equation. So we will have, of course, the GPS reference, and but we need a lot. We need to have to transpose it on the light source, on the calibration source. This reference must be transposed to the calibration source so to feed the spectrograph in order to calibrate the wavelengths. But maybe I didn't get the question fully.
So I think this is a really great topic for discussion during the coffee break.